So any questions? You have something, you want to ask? I think on Zoom, I think we see a couple of questions already. Let's address them first.
So the Excel sheet?
Excel, no, on Zoom, I see, I think Manojit has asked some question.
Oh, I told you that.
Yeah. I don't know how to. Okay. Yeah. Hello?
Yes, sir.
Okay. So why, Manojit, you want to speak, or the question was why we give voltage during JB measurements in solar cells? Right? Manojit, that was a question, right? Manojit, it's not that we give voltage, okay? We are not giving any voltage. We are actually drawing current, right, from the solar cell. So we don't give any voltage, okay? That's why, you see that, we actually, when you shine light, you're actually creating electron hole pairs, okay? And those electron hole pairs pass through the external circuit and you will have a voltage drop, but we don't give a voltage input. Is that okay, Manojit? So for example, that can be understood by your regular, if you have a regular diode, let's say like this, and then I'll have to give a voltage in this fashion, okay? Maybe some resistance and so on. Then you can characterize a diode. This is a regular operation, okay? When you're actually using it as a passive element. But in a solar cell, what happens is you don't do that. You have an external circuit. And then when you shine light on this, right? This light will actually create electron hole pairs, which will lead to a voltage drop outside in the external circuit. All right. So we do not give voltage in a solar cell. The current actually, flows to the external circuit, and that leads to a voltage drop. Got it? So how much of it and all that we have discussed, I think in week 9, I believe, when we were talking about this, right? So what we are saying is, let's say if you have no battery in this case, in solar cells, you should not have any battery. Okay. Now, if you have like this, then there is this, what is the direction of field in this depletion region? It should be in this, right? Correct? From N to P. And now when the voltage, when you shine light, you produce these electron hole pairs, and then the holes will travel in this direction, electrons will travel here. Essentially, you're going to have a voltage drop across this. Okay. And when this voltage drop is essentially, if this is some voltage V, and that should satisfy the current equation, right? Because if you have IL, that should be what? What should be the expression? I naught exponential QVA by KT. If I call it VA, okay, let's not call it VA because we are saying it's not applied. QV by KT. By KT. All right. So this voltage drop V is what falls across the resistor, but we are not applying any external voltage. Did I clarify, Manojit? Any questions further? All right. So you see that's why the quadrant also, it's not in the first quadrant. If you have a regular diode, we say, this is how your IV characteristic, is. This is your regular diode. But for the solar cell, we actually flip it. Just go and take a look at it, okay? So it's actually a current generating. It's not in the first quadrant, okay? Take a look at it, where it falls and all that. It will become clearer, otherwise we'll talk separately. Yeah. Okay. Saurabh, can we go in the Excel sheets?
Yes, sir.
Yeah. Manoj, one second. Manojit had another question here. Is it possible to use current to voltage converter as a non-inverting amplifier? No, just converter will not be working because you need to have gain as well, right? We'll have to create an additional circuit, and we can actually we can design circuits which can actually work as non-inverting amplifiers. But then you see a lot of you use op amps. They're special because they have a lot of important properties. You have the virtual grounding and then input impedance and gain and so on, everything, right? All of those properties are there which you study in the linear integrated circuits. So if you have a simple circuit, you won't have those. That's why we have those op amps which you need to build. Okay, all these linear integrated circuits. And if you look at the op amp, it contains finally transistors. There are about 27 transistors in an op amp. Okay, the simplest op amp. So if you do an analog course, analog circuits course, they'll actually teach you how to design an op amp. Okay, like the 747 you study, right? That can be built using 27 or so transistors or more. Okay, so that's how it is. All right. Yeah. Okay. All right. Yeah, Saurabh, let's go to the Excel sheet.
Yes, sir. So the first question is by Simran Agarwal, sir.
Uh-huh.
So the question is why the Fermi energy level shifts in external semiconductors?
Okay. All right. So why the Fermi level shifts? Well, for that, first, I think she means extrinsic semiconductor. I think that's what it is. I understand.
Yes, sir.
So let's say you have an intrinsic semiconductor, EV and EC. Now, if you have an extrinsic semiconductor, why does the Fermi level shift? That's a very interesting question. Okay, that's a good question because we always take it for granted, right? When we say that, if it's an N-type semiconductor, this is a Fermi level. We are used to thinking of it like this. This is if it's a P-type semiconductor and so on. We take it like a definition. It's an interesting thought process that she's able to think and ask. This is a very good question, I would say. Okay, and the reason for that is basically, we discussed this in the carrier statistics part, but I think maybe it was not very clear. So if you look back, Simran, into the week 3rd, maybe when we discuss a carrier statistic, we also introduce the concept of density of states and all that. And we say that if you have an intrinsic semiconductor, okay. So if I have an intrinsic semiconductor like this, we show the carrier density profiles. Okay. For example, here, if I talk of density in this y-axis, this is the increasing carrier density. Okay. Sorry, increasing energy. This is energy, and this is carrier density, let's say. Okay. What will happen? Basically, we said that the carrier density N is going to be a product of the density of states function and the Fermi integral and dE. I mean, we didn't go into the details of all this, but we said that eventually it is going to be something like this. The carrier density will peak and it will go. Okay. The peak carrier density will be slightly inside the conduction band. And similarly, it will be slightly inside the valence band. These are for holes. This is hole density. And this is electron density. Okay. Well, what we are saying is all of that we are kind of clubbing. We say that, okay, the peak is more or less close to the conduction band. So we say that, okay, conduction band has a lot of electrons and valence band has a lot of holes. That's what we are saying. This is for an intrinsic semiconductor. But when we say extrinsic semiconductor, we are doing something different. We are actually replacing, if you have, let's say, this silicon lattice like this. Okay. We are replacing some of the atoms with, let's say, phosphorus. Okay. If I take an N-type semiconductor and replace this with phosphorus now, what will happen? This is phosphorus. Okay. P. Now, phosphorus has 5 atoms in the valence shell. Whereas all these guys have 4 atoms. These are all silicon atoms. And they're bonded with 4 neighbors, right? Like this. So each, if you look at silicon atomic configuration in the outermost shell, what will it be? It will be, okay, 1s2, 2s2, 2p6, 3s2, and 3p2, right? So this is outermost shell. This is my outermost shell, and there are 4 electrons in the outermost shell. So we know from our basic chemistry that if you have 4 atoms, it is not going to be, it should be 8 atoms for a stable element, right? 8 electrons, sorry. 8 electrons for a stable element. So now what silicon does is, these 4 electrons from each, right? This will have an electron, and they share basically. Each atom will have 4 electrons on each side. And so these 2 atoms will share an electron pair. These 2 atoms will share an electron pair and so on. So basically each atom will effectively have 8 electrons surrounding it and it will actually be stable that way. Okay, that's how you have the silicon lattice. Now what we are doing is, we are actually introducing an element like phosphorus, which has 5 electrons. So now 4 of those electrons from phosphorus will be in the neighborhood. They'll be bonded. They'll be used for bonding because it's a valence of 4. There are 4 bonds. Each silicon is bonded to 4 other atoms. But the remaining electron now is completely free to move about wherever it wants in the lattice. All right. So because of that, you'll see that let's say if you dope it with phosphorus, you're having additional electrons. Okay. And it will also turn out, because of thermodynamics, that if you draw how the carriers are distributed in silicon, you will see that the density increases and the hole density reduces. Okay. And so we say that basically now the Fermi level is going to be where is the probability of finding an electron to be half, right? The energy level at which the probability of finding an electron is half. Now, since we are introducing electrons into the conduction band, the probability is going to shift towards the upper side. Correct? Do you agree that when I have an electron freely moving about, the carrier density increases in the conduction band? Murali, you want to answer that? You want to think about it? Or anybody? I just want you guys to talk because I'm talking from one. It should not be a monologue. I don't want it to be a monologue. Yeah? Understood, right? So the reason is basically, when do we say carrier is in the conduction band or the valence band? Physically, remember, valence band and conduction bands are simply constructs that we are using to understand what is happening. Okay. If you look at the lattice, let's say I'm thinking about this atoms arranged in a lattice here. What does it mean electron is in the conduction band or the valence band? When we say electron is in conduction band, we mean that electron is free to move about anywhere it wants on the lattice. That means electron is in conduction band. And what does it mean electron is in the valence band? That means it is bonded to the atoms. It's part of this pair that I talked about, right? I said these 2 electrons are shared between 2 atoms. When the electron is part of the bond, it cannot move anywhere it wants. It has to be confined between the atoms. And then we say that electron is in the valence band. Okay.
Unbounded, no, sir.
Sorry?
It means unbounded electron, no, sir.
Unbounded means conduction band.
Oh, okay. Free electron.
Free electron is in the conduction band. Whereas if you talk of an electron which is part of the bond like this, there are 2 atoms, right? 2 electrons in between each atom, right? That's what we're saying. That's what forms a bond. Okay. So now if it's part of the bond, it cannot move anywhere it wants. For example, electron cannot be here. Correct? It has to be part of these bonds. When it is part of these bonds, it is said to be in the valence band. Now, how will the electron which is part of the bond becomes completely free? You have to break the bond. Correct?
Yes, sir.
How will you break the bond? How much energy do you have to give to break a bond? In this case, 1.12 eV. Okay.
Yes, sir.
So if you give
13.6 by n square, no, sir.
That is an approximation. 13.6 by n square is basically for hydrogen atom. Okay. This is for hydrogen atom. There will be a correction for silicon. Okay. And it's slightly more complex. Effectively, it will turn out to be 1.12 eV. Okay.
Yeah. Because for 1.2 and for germanium 0.786, no, sir.
Yes. 0.8 is what I remember. 7.8 something. Yeah. Right. So the deal is, see the difference. This is what we call as hydrogenic atom. That means you have a nucleus and electron surrounding it. It is what happens. But now you are no longer talking about a single electron like this. Correct? You're talking of an atom which is lots of electrons which are interacting together and forming bonds. Right? I'm sorry, Talapsaya, right? Who's speaking?
Yes, sir. Yes, sir. I'm on.
Did I say the name correctly?
Yes, sir. Correct, sir.
Yeah, Talapsaya. So basically, see, we are moving away from those electronic levels, right? When we say this 13.6 by n square, we are talking about these energy discrete levels, like single atom, particle in a box kind of problem. From there, we have come to the bands, energy bands, right? Each of these basically contributes a bond, and we discussed that in the first week. Wherein, if you bring the atoms closer, right, atomic distances. If you bring the atoms close, you actually have this hybridization that happens, and then you have bands that are formed. Okay. So this is different. In this case, 13.6 by n square works very well. Okay. But here there are some corrections, and after all of that calculations, we are telling you that it's going to be 1.12 for EV, 1.12 EV for silicon. All right. Is it clear?
Yes, sir. Clear. Thank you, sir.
All right. Yeah, sure. I think I answered the question. Yeah. Sorry. Yeah.
Yes, sir. Like a continuation to that question only.
Mhm.
On YouTube, Nishita Singh asked, like,
Uh-huh.
how do we know if we do phosphorus
Mhm.
and a particular semiconductor with phosphorus,
Mhm.
say in conduction band or something? Like, how do we know that there is an increase in number of electrons physically?
Well, physically. Okay. So you can use any of the fifth group elements, right? Because Nishita, you look at my first week, right? I think I'll try to pull it up. I think I discussed it in the first week, probably even first lecture itself.
Donor elements, no, sir?
Donor elements. Exactly. So basically, if you use any of these donor elements, these are having 5 electrons in the outermost shell. That's why we know that it's N-type semiconductor. If you use P-type, these are only having 3 electrons in the outermost shell. So we can use, we get P-type doping with this. All right. And I also said, you can actually have even more complex things, right? For example, you can have group 2 and group 6 elements also, semiconductors, cadmium selenide. Okay. Things like that. You can have other semiconductors, but silicon is the most prominent one we are talking about in this course. All right. Nishita, did I answer your question?
Sir, I mean, I don't know if that is what exactly she wanted to ask, but let's say if we are doping it with some element, phosphorus or boron. So physically, when we talk about in the fabrication or in a fab,
Okay. Okay.
so how do we do that, and what exactly is the process?
Oh, well, okay. Physically, you want, how do we know that we doped phosphorus in the conduction band? Well, no. See, remember, we are not doping phosphorus in the conduction band. Okay. We are doping the lattice, the structure, right? For example, here, we should not say, we are putting an atom in the lattice. We are not putting it in the conduction band. The electron is, as a result of putting an atom here, the electron is in the conduction. Just I'm clarifying that, we should be precise when we talk about, okay?
Yes.
Yeah. But physically, what is happening? How do we know this? Well, there are ways by which you can do it. You can actually accelerate ions and then we pump it. We put it on the, we accelerate these ions and then hit those ions with make them impinge on the semiconductor. You can actually dope it. We call this process as ion implantation. But if you have a bare, if you are preparing a substrate, basically silicon is prepared by melting, somewhere I mentioned about it, I think in the course. We melt sand, it goes through a process, purified. And then in that process, you add a tiny amount of phosphorus. Okay. Then it gives you doping. How much tiny? When I mean tiny, how much? Right? If you think of the atomic density of silicon, atomic density, always I refer to this, no? Atomic density is about 10 power 22, let's say. Okay. If you want doping concentration of let's say Na equal to 10 power 18. Okay. So essentially 1 in 10,000 atoms will be phosphorus. Okay. That's why it is a very tiny impurity we are adding. We are not really changing the electronic structure. Remember, when we talk of these lattices, right? When we showed this lattice, very, very few atoms in the lattice are doped. If you put all of them as phosphorus, then the material property itself will change. Okay. So in practice, you'll never see doping densities like, 10 power 21, 22 and all. Very high doping densities is very hard to achieve. Okay. Am I clear? This is a very subtle point. You can't reach, unless you do some specialty, but even if you do that, there are some other problems that come in. Okay. Typically 10 power 18, 10 power 19 is where we stop. Even if you have 10 power 19 donor atoms, the amount of atoms that are ionized actually is lower. Okay. Anyway, that's all too much of detail for you guys. Okay. Zokratsky process. Yeah, Kushagra, that's right. Yeah. There are a couple of that one, and what is the other one? Float zone, right? Yeah. There are techniques that actually used to actually dope it, but that that you do only when you are actually preparing the substrate. But then, for example, if you want to make a MOSFET, you have N plus and P, right? Let's say. How will we get this? This sort of a thing is achieved by what is known as implantation. Okay. In the early days, in the 60s and 70s, they were using what is called as diffusion. But then nowadays, I think it's all implantation. Okay. There are different techniques that are used. That's an entirely different course in itself. Yeah. Okay.
Yes, sir.
Yes.
Uh,
Doping is only, Kushagra, just okay.
Yes,
the processes that you're referring are only for doping the wafer entirely. Okay. When you make a MOSFET, you will actually have, you have to only dope certain regions in space, right? That is done usually by what is known as implantation process. Or in the olden days, it was diffusion. But diffusion again is, there are some limitations to that. Let's not get into all that. Okay. Implantation is a technique that most of them use. What we do is, let's say you take silicon atom like this. Okay. Let's say you want to dope this area with some N plus. Let's say this is let's say P-type substrate. I want to make it N plus here. From the top, this is the top view. Okay. If I want to do this, what I'll take is, I'll take, let's say, arsenic, and then I'll, accelerate those arsenic atoms, and then they become ions, and those ions basically impinge this from the top like this. To make sure that only in this area you actually have the implantation, rest of it you cover with some mask. Okay. You cover the rest of area where you don't want the arsenic to be there by a mask. And then only where you want the arsenic atoms, open the window like this. Okay. Through that, arsenic atoms will hit the substrate and then they dope that particular region.
Positive photoresist, sir.
Sorry? Positive photoresist, negative photoresist. Well, implantation, actually, you don't use photoresist when you have to use what is known as hard mask. Anyway, yeah. For now, it's okay. Yeah. That's called lithography process. Yeah. You're right. Yeah. Talapsai. Yeah. All right. Okay. ABC is back. Last time also ABC was there. Who was ABC? I forgot his name. Bhuvanesh was ABC, I guess. Okay, anyway. All right.
If you don't mind, can you elaborate something about implantation, sir? Difference between implantation and diffusion, sir.
Okay. Saurabh, how are we doing on the time? So just, try it. Okay, I'll just do it quickly. Okay, guys, we have, I think, about 6-7 questions left. So I'll try to quickly do it. So Talapsai, what happens is, diffusion means essentially, let's say you somehow have opened the window, okay, like this. And then you have basically, let's say you want to dope this region. So you have covered everything else. Okay, this is the basic process. Now, diffusion means, see, for example, what happens when you put this wafer, let's say you take this wafer and put it in a chamber, okay, containing lots of arsenic gas. What will happen? Talapsai, what do you think will happen?
Means what and all unprotected area will not react, sir. The protected area will get react.
React in this case, even if it doesn't chemically react, right? If it chemically reacts also, there's a problem. For example, it forms a silicon dioxide. You put in a lot of oxygen, it forms a silicon oxide. Okay.
Yeah. So we need to clean room standard. Okay, sir. Yeah.
So basically what happens is, let's say you have, this is a cross section view. Okay. These are all silicon atoms. Now, if you expose it, let's say in this part, I'll have a mask. And this part I'll have a mask. Only in this area I'm exposing. So basically your, let's say, arsenic atoms have to come inside this lattice, right? Some silicon atoms have to be replaced by arsenic atoms, correct?
Yes, sir. That layer will form.
No, layer will form, or actually it will go into the lattice. It can diffuse through the lattice to some extent. Okay.
Yes, sir.
But if you do it at room temperature, you can't diffuse it to a large extent. When you melt it, it's a different thing, right? But if you want to diffuse it after fabricating, you can't melt the whole substrate, right? You can't dope it by the, what Kushagra was saying, Czochralski process and all that. We can't do that. So we cannot melt it entirely. So we open this window and let it diffuse, correct? But if you do it at room temperature, the diffusion is very, very slow. I mean, very, very slow process. You have to reheat it to, let's say, 700 degrees, 800 degrees centigrade for the diffusion to be fast. Okay. Then essentially the gas will diffuse faster into the substrate. But eventually it's going to be limited. Okay. So what we do is, that is a very, it's okay to use it in the earlier days, but nowadays we want much more precise control of the doping. Okay. So we use what is known as implantation process, wherein we don't depend on the, it's a slightly lower temperature process. You don't have to heat it up to 700, 800 degrees plus. Okay. What we do is we simply accelerate ions, and then with high energy, they hit this substrate and they go inside. Okay. But then they also, damage the crystal to some extent. So we have to do some annealing processes and all that after that. But that can be done. So with this, we can actually get much higher, we can actually implant much better. Okay. Much higher densities can be achieved. That's why we have moved towards implantation most often, especially in the device, front end of the line. I think it's implantation. diffusion is, it's very, I think, yeah. All right. I hope I answered your question. Yeah, let's move on, Saurabh. Next one.
Thank you. Thank you.
Thank you. Yeah. Guys, anybody has questions, please feel free to, write in the chat, okay? We are happy to answer. Yeah.
Yes, sir.
Talab sir, you said you're not able to see my screen. Is it okay now?
No, it's okay, sir.
All right. Okay. Sure. Yeah.
Internet problem, sir.
Okay. All right. Yeah. Yeah.
Sir?
Bhunesh.
Bhunesh. Yeah. ABC. Yeah. Tell me.
I have a question, but in FinFET, we have a better electrostatic control, right, sir? How it is possible?
In FinFET, how will you have better electrostatic control?
Yes, sir.
Okay. So see, I mean, MOSFET, traditional MOSFET is this, okay? Let's say like this, flat. Now you're applying voltage only from the top, okay? But a FinFET is like this, three-dimensional device, right? So this is my silicon, and I have an oxide around it, and I apply a gate around that. So now if the fin is very, very thin, then I can have channel on this side, and I can control very much better when you have a three-dimensional structure. And we mentioned last time that actually the ideal case would be the gate all around transistor, which is even like a pencil, right? You have gate all around it, you can actually have even much better control. Yeah. Did I answer? Bhunesh?
Yes, sir. Slightly voice is breaking.
Saurabh, is my voice breaking?
No, sir, it's fine.
Maybe then, Bhunesh, maybe it's on your end, maybe the speeds and all that, no? Yeah. Saurabh, let's move on, yeah.
Yes, sir. So there is one more question. Actually, there are two questions by the same person, Rubini. So the first one is, what will be the flat band voltage of MOSFET if there is no gate voltage?
Flat band voltage of MOSFET?
If there is no gate voltage applied.
No. See, flat band voltage is basically, okay, let's see. Let's take the example of MOSCAP. Who asked this question?
Sir, Rubini.
Rubini. Okay, right. Okay, so the deal is this, okay. What is flat band voltage? First of all, okay. When, we talked about the MOS capacitor, right? Wherein we said we have this oxide and there is this, let's say some P-type semiconductor like this. And there's an N-type semiconductor. Sorry, the metal like this on this side. Okay, this is metal, EF of metal. And this is my EF. Okay. So now, if you have, this is a flat band. Okay. But if you have some non-ideal metal, okay, that, the work function of the metal is different. Okay. Non-ideal MOSFET, if you have. One of the non-idealities is that EF of metal is not equal to EF of semiconductor. Okay. If you have such a scenario. Now, what will happen? Now, let's consider a situation where I'll move this guy up. I'll do like this. Okay. So clearly, I don't have the work function of metal is different from the work function of semiconductor. In effect, what should happen is some electrons should go into this side. I mean, intuitively you can think, but externally, I mean, you'll have a circuit which completes this, and because of that, it happens not through oxide. But we can think of it like that. Okay. Once you have this non-ideal metal, now your bands cannot be like this, because now you can think of this as a high, it's higher level, right? Energy level. So electrons will flow. I mean, you can think of it like that. So then what will happen is your bands now have to be like this. Okay. It will not be flat anymore if you don't apply any voltage. When there is zero voltage applied, it has to be like this. Why am I saying it should be like this and not bending upwards like this? Not like this? Saurabh? Why this is not allowed? The reason is, if you do that, this means that there are more holes here, not electrons. So when you have electrons, effectively it should bend downwards, so that if you look at, at concentration of the electrons in the bulk versus concentration of electrons at the surface, it will be different, right? There are more electrons at the surface related to the bulk. That's why we are saying the band is bending this way. So now when this happens, you have to apply a certain voltage to bring it back. What kind of voltage will you apply? Yep.
Look.
Hello?
Yes, sir.
I would actually apply negative voltage. All right. Does it answer your question? I think, I don't know, they're live or not.
No.
Okay.
Sir, the same person has one more question.
Mm-hmm.
If the MOSFET technology mentioned is 180 nanometers, will the channel length be 180 nanometers?
Well, I think I talked about it in, maybe in the week 8 or week 10, maybe when we talk about the scaling, right? In the olden days, before 2000, it was true. Okay, when you say 180 nanometer technology, the channel length was more or less 180 nanometers. But then I think starting about 2005 or so, or even slightly earlier, the channel lengths are not able to keep up with the technology names. Okay. So I think I have talked in detail about the scaling part in week 10, I believe. Okay. If you look at it, we have mentioned it somewhere. Well, when I talk about the scaling, right, this is all, we talk about it. And I say that, no, in the earlier days, the pitch was, the channel length was close to the, excuse me. Nowadays, I think it's no longer true. Okay. Now the channel length is much larger, or, the physical dimensions have changed and a lot of things have happened. But still, we like to follow the same convention. So effectively, you can think of the, the node, technology node defines how much advanced the process is, that's all. Okay. We are not able to keep up with the same physical dimensions. In fact, actually the technology name, right, 250 nanometers, 180 nanometers came from not the MOSFET, but from the DRAM technology, wherein the half pitch, if you have two DRAM cells, so in that half pitch, what is in the memory, what is the distance between them? That was the best technology. That quantified how good the technology is. So people started using that number. Okay. But anyway, now I think it has no physical meaning except, we are still paying homage to Gordon Moore and his law. Yeah. Yes, Nishita Singh has follow-up question, I think.
Yes, sir. I was going to ask that one.
How do we know that phosphorus is diffused between 4 silicon atoms? That's a very interesting question, Nishita. So see, it may not be right in between. Like, there is no reason. It's not actually a silly question. It's a very good question. So, okay, let's say you have silicon, 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 silicon. Sorry, I should not do this. I'll change the letters. There are silicon atoms like this, right? How do you know that you're going to replace one of these with phosphorus? Why can't be phosphorus here? Right? So it turns out that that's what, you don't have to do anything much. If you diffuse automatically, I'll say that it will go in this region because that's where the energy will be minimized overall. No, Nishita, I'll actually ask you for a different question. Okay. I'll say that why do the silicon atoms form those lattice structure? It's a very amazing thing. No, if you think about it, this distance, I don't know, silicon lattice constant is what? Somewhere I think we did 3 angstroms to 4 angstroms or something. I forgot the number. Saurabh, can you just quickly Google? Some number will be there, no? Bond length in silicon? Some 3 to 4 angstroms. 5 angstroms. 5 angstroms. Okay. So 5 angstroms. If it's 5 angstroms, and that is like, you have millions of atoms, billion atoms, right? If you say 10 power 22 atoms per centimeter cube, think about the scale, no? In 1 centimeter cube, you have how many billions? 2 billions? No. It's actually what? Roughly million, billion, billions, I don't know, or 2 trillions, 2 trillions, right? So many of them. Okay. So, and all of the distances are exactly 5 angstroms or, 5 point something angstroms. It's an amazing thing. Why does it form that? Let's say you take germanium, the lattice constant will be different. Why does that happen? Okay. We can compute the total energy of the system. Let's say if we put these atoms together, and then compute the total energy, and you will find that the energy will be minimum when this distance for this particular set of atoms, for silicon atoms, we can actually, we talked about these potentials and so on. If you talk about these potentials, right, like this, for each silicon atom, it's like, positive charge, which is attracting an electron around that and all that. You can compute the total energy, and it turns out that for those particular lattice constants, the energy is minimized. So to answer, Nishita's question, if you have this phosphorus somewhere else in between, for example, say somewhere here, the energy will not be minimized. So automatically phosphorus will try to go into one of these states. But if you do implantation, it can actually come in between. Sometimes it can be somewhere in between here. Okay, it's not going to be minimal because it's a low temperature process. So after that, we do a step called annealing. Let's say, for example, just after the implantation, maybe the phosphorus atom is somewhere here. And then we do annealing, what is called as annealing. Immediately, it will go into one of those lattice sites. Okay. We don't want it to be in between the lattice site. We call this as interstitial. If you have somewhere in between, it's not good for us. It will destroy. It will not, really properly. It will not give you good electrical properties. So we would like it to be on this lattice site so that it shares these 4 electrons with the neighboring silicon atoms, and then one is free. All right. Yes, Nishita. Yes. You have to complete the octet and so on. Yes, correct. All right. Yeah. Let's move on.
Yes, sir. So Akshay has a question, sir. Like, in
Akshay,
what areas?
Hi, Akshay. Yeah, good.
In what areas do you think photonics will complement electronics?
In what areas? Photonics, I think, is now increasingly becoming central to everything, right? Communications is all photonics, isn't it? You guys don't realize it, but communications is all photonics. Okay. Because if you have electronics, you will not have this instantaneous communication, right? You can video call to somebody in US and so on, right? That won't happen with electrons. Okay, it takes a finite amount of time. So it's all long distance communication is all photonics. Now, that should come onto the chip. Okay, now it's come to your home. The fiber optical signals have come into the home. It has to come onto the chip now. Okay, because see, I mean, nowadays the problem is, I think maybe I mentioned it last time, and I sometimes lose track of which course I'm mentioning this in. Now, let's say you have the chip like this on your, in your processor and so on, right? You have these computers. Let's say you have a chip. The question is, you have amazing computation capability here. Think of a graphics card. Okay, let's say that's very, very good computation engine, right? But then it has to interact with the neighboring peripherals. For example, the memory and so on, so many buses, so many things will be there. No, the data has to come from outside. Now it has come to a point where the amount of power that is required to bring the data from outside into the chip for performing the computations and actually sending it back, that has become a significant part of the overall power consumption. Okay. Now it's increasing greatly, and you don't have enough bandwidth to bring the data in. Okay. So now if you can actually bring it in by photonic signals, that can be much more efficient. And now people are talking about what they call as, co-packaged optoelectronic devices, wherein you talk of chips plus photonic devices packaged right now. Okay. So I think it's going to be complementary signals, as Kushadra says. I think photonics and electronics are very complementary, and they'll go hand in hand. No, you think of lasers, you think of solar cells. There is some amount of photonics involved there. Lasers is entirely optoelectronics. Okay, you can't even you can't even think of this long distance communication that we have with optical signals, right? Without lasers, it's central to everything. Yes. All right. Everything, yeah, photonics complements everywhere. Yes, that's why I don't. No, I think these are all names. Okay, as initially, because when you study, right, you have to have these neatly segregated subjects and civics, mathematics, and so on. But then you as you evolve in as you go deeper and deeper into something, you realize that everything is related. Okay, for example, in nowadays, in you might say that what has mechanical engineering, what has it got to do with electronics? Okay, but you'll see that a lot of heat is dissipated, a lot of thermal issues are there in electronic devices, and a lot of mechanical engineers work on that. How do you develop cooling systems, active cooling systems, and so on? Okay, so I think science is it's a very broad thing. Somehow in our country we think that science is bad and engineering is great, but science is it's a very general thing. It's very, very broad. It just you go by your curiosity. When you keep digging and digging and you go deeper and deeper, you'll realize that everything is interrelated. Okay, and when I talk about in week 11 and 12, when I talk about optoelectronics, you will see that the way an electron behaves in a semiconductor is closely related to its optical properties. All right, so I think they're all related. Yes, I think I answered the question. I think Saurabh, let's move on.
Yes, sir.
Because I have a hard stop at 5
yes.
maximum. Okay.
So, there are 2 questions by Lakshmikanta Mishra, but
Okay,
I think he's online. If he wants, he can ask the question.
Lakshmikanta, yeah, sure. Or if it doesn't prefer, you, Lakshmikanta, you want to speak?
Yes, sir.
Yeah, tell me.
So actually, during the MOSFET saturation, so when the channel gets pinched up or tempered, it becomes more and more tempered. But Utah told that it does not affect it acts as a constant current source, where VDS does not affect. So if VDS is not affecting, how the electron is traveling without any channel?
Lakshmikant, I think you had this question last time also, I think, and I didn't get the time to answer, I believe, right?
Yes,
I got distracted. Yeah, I'm sorry about that. So the reason, it happens is, let's say you're talking about a MOSFET like this, and let's say you have this, pinch off, right? Happened. Now the question is, this voltage, right? If I think about it, what is VD sat when this pinch off just happens, isn't it? In the traditional long channel MOSFET, this will be VD sat, correct? This will be VD sat, correct? At VDS equal to VD sat, it will happen. You agree with me, Lakshmikant?
Yes, sir.
So now what we're talking about, it is voltage is greater than VD sat, correct? So what happens is, now in this case, when you actually VDS is greater than VD sat, you will have some region in the channel. I mean, remember I told you that this is exaggerated picture. It's effectively that this density is different. That's it. Okay. Let's say this is my overall, this is grounded. This is my source. This is my VD. Okay. Voltage at the drain. Now VDS is greater than VD sat, let's say. Okay. So now voltage drop across this region will be VD sat. Now the voltage drop in this region is going to be how much? VDS minus VD sat. With me so far?
Yes, sir.
So now what's happening in this case is, what happens to a carrier here? Like, for example, you apply positive voltage, right? So now carriers can actually drift across this region. They experience drift because there's an electric field in this region, correct? And because of that, whatever carriers are available here, it will just drift. Okay. And that is why when we derive the current density equation, the square law equation, right? We looked at the total amount of charge. The total amount of charge remains the same, but whatever is available, it goes across. Okay. So there's no further increase in the current. You follow my point?
Yes, sir. Yes.
So that's why we are saying when we draw the ID VDS, right? ID versus VDS, initially we'll say this is increasing, and then at some point it saturates. After that, it doesn't increase is what we say. In the classical long channel MOSFET, it happens. Okay. It doesn't increase because you're not having any additional carrier density. Finally, the density of this is what is going to determine how much current flows. Okay. Now the channel got pinched off. There's no further, additional electrons that are coming in. Let's say if it's an NMOS. All right.
Yes, sir. Yes, sir.
So now that amount of electrons are effectively being dragged across by this field here. Okay. The drift. All right. And because of that, you will have limited current like this. Actually, there are other things that come into picture in the short channel MOSFETs. And I think I mentioned briefly channel length modulation also. It increases like this. But anyway, that's a secondary effect, short channel. Okay.
Yes, sir.
Okay, good. Lakshmikant, you had another question?
Yes, sir. This is also just fundamental question. So basically during scaling, so in a long channel MOSFET, the depletion region under the source and drain, we just neglect it. But when we scale more and more and more, that the depletion region between the source and drain are now prominent, and we take into account so how it affects the threshold voltage and the CV characteristics.
Okay, the deal is, okay, I mean, this is a very interesting question. And, yeah, I mean, when we talk about the old transistors, we'll say this, this is we used to call it as, let's say this is source and this is drain, right? And they used to call it as L drawn. Okay. Drawn means basically what you do in the GDS file and all that, when you fabricate the transistor, how much you designed it to be. And your channel length was that. Okay. But, because this was very, very small. Okay. Okay. So now, when this was like 10 microns, and this depletion region typically will be less than what? 100 nanometers, typically 100 nanometers, 200 nanometers, something like that. It was very, very small compared to the overall channel length. Okay. So we ignored it. But when we come to the short channel MOSFETs, this is itself, let's say the length itself has become 250 nanometers. Now the depletion width will become significant part of it. So now effectively nowadays, if you look at, when we try to model these devices for technology, we talk of something called L effective. This will be L drawn minus 2, let's say XD, the depletion width. On both sides, I have depletion width, and that can change with voltages and so on. So it becomes, there is an, the length will be slightly different. Yes, of course. Yeah. Okay. And there's also overlap that happens, overlap capacitance and so on. Overlap. Anyway, let's not get into all of that. Yeah. Okay. So these are, what was the exact, so you said, this happens. What was the last part?
The threshold voltage. Will it affect the threshold voltage?
Yes, it does. It does. Okay. So now what happens is, now if you have a depletion region here, let's say the depletion region, now you don't have to invert this part. Finally, if you have a long channel MOSFET, the threshold voltage we are calculating, right? That expression, surface potential plus, the gate oxide, right? You have the threshold QD by Cox plus what? What's the expression for threshold voltage?
So V flat band minus Qox by Cox plus 2πfm, something like that.
2πf plus QD by Cox. Okay, then there are some, non-idealities, if you have a flat band voltage difference and all that. So now 2πf plus QD by Cox, right? So now that is not having any channel length, correct? So now if you have a short channel MOSFET, what happens is, you can think of it like this, you have this part of the channel, which is already depleted, right? You don't have to apply additional gate voltage to deplete part of it, no?
Yes, sir.
So what should be the threshold voltage now? Slightly lower.
Lower, sir.
Lower. So as you have this, go to smaller and smaller dimensions, short channel effect, the threshold voltage reduces. I think I discussed this part. I think I have done it in, very quick way. The,
yes.
The width, with what happens with length, short channel, long width, right? Narrow width. What happens? In the case of narrow width, we said it actually increases. Okay. Why it is, you have to think a little bit about it. Go and look at that part of the video. I think it will become clearer. All right.
So is there some mathematical formula that how much it will reduce?
No, this becomes, empirical, because there are too many effects there. Generally what happens is, see, for us, when we study semiconductor devices, we write these nice equations, ID is equal to mu Cox W by L into VGS minus VT whole square and all that. That works, in the olden times, but nowadays, things are so complicated that you actually model all these things with what is known as SPICE simulators. Okay. BSIM models is. So basically in those models, those are semi-empirical models with some amount of physics, but a lot of empirical parameters. You require about 200 parameters to describe a MOSFET nowadays. Okay. So it's a pretty intense thing. It's not that simple as what we are seeing. But, these are actually the physical phenomena that actually impact. Once you understand this, you can always use a computer. You do the first part, you understand some amount of by intuition. Rest of it, you actually look at the actual devices and look at model it and all that. There are semi-empirical models that come in. And all of that, together is called as compact modeling. I don't know why they call it compact modeling. But, it basically have, one of the popular ones is called BSIM. BSIM, okay, it's a SPICE model. SPICE model. It's a very old, simulator that was built out of University of California, Berkeley, I think. It basically simulation program for integrated circuits, something like that. Okay, SPICE. So you have a parameter BSIM model, which nowadays modern MOSFETs will have 200 plus parameters to completely describe it. And it's semi-empirical. Some physics is there, but it's not entirely physical physics. Okay. Yeah. Let's move on.
Okay, sir. Thank you, sir.
Thank you.
Sir, continuing the discussion on the defects and VT, reduction of threshold. Piyush asked what if we introduce some defects in the oxide, then VT will reduce. So can we do this type of thing in practice? I mean, do we want to do this type of thing in practice?
Okay. So the issue is, Piyush, if we can't even say that it only decreases, but you can have different type of defects, right? If you have a positively charged defect, if it's an NMOS, it reduces, but PMOS, what happens? If you have positive charge defect, it will repel the holes, right, from the inversion layer. So it actually increases the threshold voltage in a PMOS device. All right. And the other problem is these are not very easy to control. Okay. So we generally don't try to introduce defects, and we don't try to control the characteristics by this, because even if you have all these traps and all that, sometimes carriers can actually trap in and trap out. Detrapping also can happen. Because of that, they can be unpredictable results. Now, for example, if you look at the when we initially in the 1960s and 70s, right, people started sending rockets into the space. One of the problems they found was you have all this high energy radiation in the space. Okay. Gamma rays and X-rays and so on, high energy radiation, they don't reach Earth because you have ozone and you have the nice atmosphere which is protecting us. So we are safe on Earth. But if you go into the space, there's a lot of other radiation that comes in. And remember, if you have an oxide, we say it's a band gap of 9 eV, right? But if you have a high energy, let's say, X-ray or something like that, it can actually cause an electron hole pair to be produced. It can cause a defect. It can break a bond and so on, right? So when you have a transistor, you have this nice, source, drain, and so on. But let's say if you send it into space, now the X-rays will actually cause some defects to come here, and then that will cause threshold voltage shifts. Okay. So there's a lot of study that was done in the late 70s and early 80s to make what are known as radiation hard devices. Basically, you don't want them to suffer from radiation. Okay. And because the radiation actually causes, you do such a careful design with billions of transistors and build a processor. The moment you take it into space, it doesn't work because some random events will happen. Okay. So there's a lot of study done to prevent these things. There are other considerations as well, but anyway, yeah. So we don't I think it was Piyush, right? Piyush. So we don't want to use these things to actually
Yes.
control.
Kushagra had a question.
Yes.
That like if we have a piece of unknown semiconductor, how can we determine whether it's a direct or an indirect bandgap semiconductor? Physically, like do we analyze from the dispersion diagram, or what do we do?
Kushagra, I answered this question in the other course. Okay. So basically, we talked about the absorption. Okay. We talked about H nu versus absorption coefficient, right? Alpha versus H nu. And then I said, for a direct bandgap semiconductor, it will be like this. I mean, for others, okay, just ignore it. I mean, it's something, I'm parallelly teaching another course. So in that, I talk about all this. It's okay if you don't understand. Essentially, what I'm saying is alpha is absorption coefficient is equal to some, or rather some C times E minus H nu. Sorry. H nu minus EG whole square root. Okay. So if you take plot alpha square versus H nu, you will see that the intercept is going to be EG and energy absorption increases. Okay. If you have a straight line, it's a direct bandgap semiconductor. But if you have a thing like this stretching out, that's an indirect bandgap semiconductor. So you can take a piece of semiconductor, shine some light at different wavelengths, and look at the absorption. And looking at how absorption is changing as a function of wavelengths, you can determine whether it's a direct or indirect bandgap semiconductor. Right? Yeah. So next one. Oh, there's somebody Bond. Ryback Bond. Huh? Nice to see you, Ryback Bond. What does that mean? Ryback? I don't know. It's very interesting. Anyway. Yeah.
Yes, sir. So we have one question on YouTube, sir. Bhuvnesh asked.
Yeah.
I don't know if he's all right.
So Bhuvnesh, ABC will be here, I guess. Yes. I mean, he'll be watching. I mean, he is like.
Yes.
Yeah.
So he asked, like, what happens if we use undoped silicon in photodetector?
Okay, Bhuvnesh, that it's the story is a little bit more complex. Okay. So we actually use. Sorry, let's just give me a minute. Yeah. We talk about the PIN junctions, right? PIN diodes, we said. Remember in the, I think, photodetectors part, I talked about this, wherein I have this, and this is intrinsic. This is undoped. Okay. The reason for that is a little bit more complex. What I'm saying essentially is that you have the highest generation rate when you have this carrier density. Okay. When you have intrinsic semiconductor, you can have large carrier density. Okay. Sorry. No. That's not what I mean. We essentially, when you shine light, right, you want to create electron and hole pairs. Okay. When you have intrinsic region, the generation rate is going to be high. So you get much better efficiencies. photo detection. Okay. So if you have doped, that becomes, well, I mean, the story is not complete there, right? But I think it's a little bit more complex. Then let's not get into that. Okay. Because we'll have to think about a lot more factors, how the curvature of the bands are and so on. Dipanshu is saying that, yeah, it helped. Yes. Thank you very much, Dipanshu. If it helped, I'm happy. I'm not happy that it only helped for gate. I mean, I think I hope that some of you are motivated towards electronics. Okay. We need people who understand deeply. It's not about just the jobs and all that. That's okay. That's an important part of our life. But I think there is a certain beauty to it. And, for a country of 1.4 billion people, I think we should have a lot more semiconductor specialists and a lot more people who understand this. Okay. Yeah. Yeah. Let's move on. Yeah.
Sir, Kushagra again asked a question. Why do we study HFCV and LFCV?
Why do I study HFCV and LFCV? Because it tells me about how the inversion layer behaves. Okay. How does the inversion charge respond? Because finally, if you want to switch on and switch off transistors, what matters? The minority carrier lifetimes. Okay. If I study at different voltages, I can actually see, I think I mentioned this also. MOSFET CV is used as a diagnostic device. Just by looking at the shape of the CV, we can infer a lot about the physics. What we did was simply a phenomenological model where we said, okay, we have capacitor, parallel, series, and so on. Sorry, not parallel, series, right? We talked about that. But if you actually do all these, different frequencies, we just don't do one HFCV and one LFCV. We do LFCV is in fact very difficult to do. What we do is make a CV measurement at 1 megahertz, 100 kilohertz, 10 kilohertz, 5 kilohertz, and so on. So in some cases, what will happen is, we talked about this trap, right? Somewhere I mentioned this trap and so on. Okay, some of these traps respond at certain frequencies, some others don't respond. So you can infer a lot about the physics of the semiconductor device by measuring the CVs. Okay. What we did was the basic, high frequency, low frequency, but there's a lot more to it. Yeah. That's my short answer. Yeah, let's move on. Because I think we have to close. Saurabh, how many more questions?
So done, sir. There are no more questions.
No more questions?
I mean,
yeah, I mean, we can just take a...
1 second.
Anybody has, last questions, before we close? Because I'm sorry, I'm on a time constraint here. Next time I'll try to keep it more open. We'll again have an interactive session. Maybe, when is the exam, by the way, guys? I think in October end or somewhere it is there.
So 24th, I think.
24th. Huh? Okay, let's do one more session. Today is what?
29th, sir.
29th? Oh, wonderful. Okay, so we'll actually have one more session, maybe, let's say in 15th, week of 15th, I don't know. Okay. What would be good? Let's say week of 15th or even, yeah, maybe 18th, around 18th or something, we can have a session, one more session. All right. That will be good, I think. By then you could also review everything and then we can have any queries you have, we can answer. All right. All right, guys. Saurabh, you found any other questions?
Sir, there is one question by Pawan. I mean, he asked why high energy sources have less number of photons. I am not sure what he means by that.
Well, it's not which course.
This course.
This course only he's asking. Well, see, I mean, yeah, I think it's not exactly true, Pawan. Let's say, okay, maybe you're referring to this. Okay, let me say I have 1 milliwatt of 532 nanometer light. Okay, and the same 1 milliwatt of 1064 light. Okay, so same power, I have two energy beams, but wavelength is different. This is the context, I think, right? That's what I think. When we calculate this, we essentially are saying that what is milliwatt? Milliwatt means 1 millijoule per second, correct? 1 millijoule of energy. Bhunesh, huh? Bhunesh? Huh? Bhunesh, I'm sorry, I can't hear you clearly. Essentially, what we are saying is 1 millijoule of energy, right? So 1 millijoule of energy in this case divided, what is the, in EV, let's say this is, we can compute this exactly, but let's say this is, say, 2 EV. I'm rounding it off. Okay. So this is my 2 EV here. Correct. Then I get some number of photons. But in this case, same 1 millijoule of energy divided by, this is 1 EV, let's say. Okay. Equal to, say, 1 EV. Right. You understand what is EV also. We talked about this. This is going to be E, if you remove, it will be 1.6 into 10 power minus 19 joules. This will be 1.6 into 10 power minus 19 joules, right? So you can count how many photons are coming. So I think, Saurabh, Pawan means that in this case, you have lesser number of photons. Okay. In this case, you have larger number of photons, just that because for the same power, you have, the photon energy is, finally the power is going to be what? Power is going to be number of photons, let's say N, right? We call it by phi also, photon flux, right? Photons per second. Photons per second into the energy, h nu, correct? Right? So now, if you are taking a higher energy photon, of course, for the same power, you'll have lesser number of photons, right? Higher energy will give you lesser number, so that same power. That's the thing I think we are talking about. All right? Yes. Okay.
Sir?
Yes. Please. Yeah. Bhunesh, who's speaking?
Sir, you spoke about non-ideal MOSFET now, sir.
Yes.
Sir, there that we need to apply a voltage now, sir. It's due to thermal oxidation is not performed well, or it's a non-ideal case, sir?
No, non-ideality I'm referring to. I mean, there are various types it can happen. In this case, I'm saying that the Fermi levels are different. In ideal MOSFET, I assume that the Fermi level is here so that when you don't apply voltage, the bands are flat. Okay. Now, when I consider a non-ideal scenario where the Fermi, what do you call this? Work functions are different, right? For metal and semiconductor, then to bring it back to the flat band situation, we have to apply some voltage. That is why when we talk of the VT, right, we talk of phi ms plus 2 phi f plus QD by Cox and so on, right? There's one more term. What is the term? Maybe QI by Cox. Okay. So these are anyway regular MOS caps. Okay. This is a work function difference, and this is some interface trap or some trap densities, if you have, equivalent trap densities. So all of these are contributing to threshold voltage shifts. Did I answer your question?
Yes, sir.
So yeah.
In theory, there is one question, sir. Why PMOS is not used in old NMOS is not used? Why PMOS is used? It will be off at 0. It will in NMOS we need to maintain even it is off. Also.
Did we ask it in the assignments or something? Did we do that?
No, sir. I'm just relating, sir.
Okay, so that is basically, it's not even, that's not an exact thing. It depends on the, the trap density and so on, right? If I have some oxide traps, fixed oxide traps or something, or interface traps, then my threshold voltage is going to shift. Okay. So, yeah, I mean, I would not necessarily say that happened. Actually, I think, we initially had in the early, early 60s and the late 50s, I think NMOS devices were more prominent. PMOS was actually much harder to achieve. So they built what is known as NMOS inverter and so on. Even the Intel 4004 processor, I think, is mostly NMOS. It's not CMOS. Because, I mean, the other reason was also that, you have to match the threshold voltage and all. It becomes increasingly complex. It took some time for them to figure out how to do that. Yeah. Did I answer your question? Or at least, gave you some reasonable answer, right? Okay.
Yes, sir. Right. My internet connection is unstable, sir. I am able to.
Okay. No issues. Yeah. All right.
Thank you. Yes,
Thank you. Yeah, I think so. I think we have answered almost everything, right, Saurabh?
Yes, sir.
Yeah. Okay. So guys, yeah. So nice. Thank you so much for, attending this, and, I'm happy to interact. I love this. So let's do it one more time. I mean, I think we have, we can do as many as you want. If you want, write emails and then we will schedule it separately also. I don't mind at all. Okay. We can even do one-on-one sessions if you like, whatever you like. Okay. See, for one of the first things for learning is to get over this fear. Okay. That I don't know or something. Oh, this is a silly question and all that. Don't have any such fears. It doesn't matter. Ask as much as you want. What is the worst thing that can happen? I'll say that I don't know. Okay. I'm going to learn. I'm happy to learn. I think I was mentioning last time also that, when I teach this, see, I have taken this 2-3 times, maybe these courses, but when I took it, it still doesn't fully get inside. When I start teaching it, it becomes more and more clear to me. Okay. If you ask me some interesting questions, I'll try to find out answers. Somebody asked me at some point, why is the effective mass of holes larger than effective mass of electrons? Okay. We simply take it for granted. Effective masses of holes are higher. But why should it be physically? Can you intuitively explain? Okay. We have a good explanation for that actually. But anyway, you think about it. I'll answer it if you think about it. Next session, I'll answer it. Okay. If you still think about how the electrons are moving in the conduction band and how holes will move. Holes means basically lack of electron in the bond, right? So how fast can that move with respect to, relative to the electron in the freely moving electron? That will explain the thing. Anyway, all right. So yeah, so please, go ahead and, ask as much as you want and we're there. All right. So next week, we'll try to have it on 18th or something, 17th, 18th. And please feel free and keep emailing. All right. So yeah, thank you so much. We'll close this session. Balaji. Balaji is out. Let's call him and we'll just close it. By the way, guys, I can just close it. Okay. I'll call him and tell him. All right. Thank you. See you next time. Bye. Balaji, I'm done. Thank you. Thank you so much. Yeah.